Now this one looks a little bit more bizarre because the left hand side, it looks like a first order linear differential equation. But we have this equal to y squared, so this is not first order linear differential equation. In fact, this is an example of a Bernoulli's differential equation. And let me write down the general form for you guys. We have dy dx plus some function in terms of just x times y, and this is equal to some function in terms of x, but here we multiply by y to the r's power, and r can be any real number. So in our situation here, q of x is equal to 1, which is okay, and r is equal to 2. Okay? And how do we solve this though? Well, I will tell you. We will first do a substitution, and we usually let v be our new variable, and the substitution is y to the 1 minus r's power. With this substitution, we will be able to take this Bernoulli's differential equation from the xy world to the xv world, and in that world, it will become a first order linear differential equation, and then we'll do the things that we did earlier. Yeah, so let's go and do it. So just trust this differential equation, you'll see that it works out so nicely. V equals, in our situation, we have y, 1 minus 2, so we have negative 1. Take a look right here, and then we differentiate both sides with respect to x. So we see we have dv dx, that's equal to, put the negative 1 to the front, and then minus 1, and then because y is a function of x, we multiply by dy dx. And now this is how I will recommend you guys to do it. I'm going to write this down one more time. So we have the dy dx plus 2 sine x over sine x plus cosine x y, and this is equal to y squared. What we will do is, let's multiply everybody by whatever this coefficient is, namely negative y's negative 2 power. Because when we multiply this right here, you see, we get dv dx right away. So that's how I like to do the change. And it will always be like this, very nicely. So first we will have dv dx, so let's go ahead and write that down. Then negative times that, this part stays, so we have negative 2 sine x over sine x plus cosine x. Now y to the negative 2 times y to the first power, we get y to the negative 1. But of course, if you look back, y to the negative 1 is v, so we can put that down right here. And lastly, this is equal to negative 1, yeah, because y to a negative 2 times that is just negative 1. Ladies and gentlemen, have a look. Differential equation that's linear first order in the xv world. So yeah, integrating factor. And the most important part is this part, we have to integrate that. So let's focus on this right here. So this is our little goal. We have to look at the integral of negative 2 sine x over sine x plus cosine x. And I want to show you guys my favorite technique of integration called the wouldn't it be nice. Let me show you. If you have seen my 1, 2, 3, 4 integral, you know what I'm talking about. But here's the deal. Wouldn't it be nice, since the denominator is already sine x plus cosine x, what can we really do on the top to make this integral super easy? Please do not say put a 0 here, don't do that. But the next easiest one is, of course, what if we have the same exact thing, namely sine x plus cosine x. I know this is super redundant, but it works. Because this right here is just integral of 1 in the x world, so we'll just get x. Well, is there another integral that's also super easy? Yes, because when we have the denominator being sine x plus cosine x, wouldn't it be so nice if the numerator is exactly the derivative of the denominator? Namely, cosine x here, and then the derivative of that, which is negative sine x. Because if this is a situation, then we can just do a u sub, let u equal to the bottom, and we'll end up with ln of the bottom, because the derivative is on the top already. So we have ln of the bottom, which is sine x plus cosine x in the absolute value. Now, is it possible for us to somehow combine this and that to produce negative 2 sine x? They have the same denominator already. our goal is to think about multiply this by some number and then add it with multiply by some number to produce that. This is called a linear combination. Let's see. If we simply just add these equations, or integrals technically, equation integrals, sin x will cancel. No, I don't want that. I want the sin x to stay. So what if I cancel the cosine? If I put a negative here, then cosine will cancel. Sin x plus sin x is 2. No, I want negative. So in fact, I will have to put a negative here, meaning we multiply by negative throughout this equation. So this right here should also be negative. And notice that I didn't put down the plus c because it doesn't matter for this little part. And if you look at this, because they have the same denominator, cosine x and cosine x will cancel. Negative sin x minus another sin x, we get this. So when we combine these two equations, the left-hand side does give us the integral of negative 2 sin x over the same denominator, because integration is linear operation. So we can just add inside. Very nice. So this right here becomes negative x plus ln absolute value of sin x plus cosine x. So that's how you can integrate this. Cool. But this is not it. For the integrating factor, I'll put on little if. We will have to do e to this power, e to that power, right? So here, the integrating factor is actually going to be mu of x, which is this part. That's going to be e to this power, which is e to this. And because we are adding the powers, so we can say multiply by e to this power, which is ln absolute value of sin x plus cosine x. And we see e and ln cancel, and just like our discussion earlier, the absolute value doesn't matter. Just take the positive version of that. So we're just going to say we will use our integrating factor being e to the negative x times sin x plus cosine x. Whew. So I'm just going to multiply everybody by e to the negative x times sin x plus cosine x. Before we continue, you should still believe that the answer to the differential equation is 1 plus tangent x. But anyway, first take this, multiply by that, we still have that e to the negative x times sin x plus cosine x, and then we have that dv dx. Very good. This times that, this and that will cancel, and we have a minus 2 e to the negative x, and then that sin x factor, and then times v. And lastly, we have negative 1 times this, e to the negative x times sin x plus cosine x. And now let me tell you guys how cool a first order linear differential equation is. The left hand side, it's always going to be the derivative of the integrating factor, namely that part, e to the negative x times sin x plus cosine x times v, right? Because we are using v for our variable here, guaranteed. And this right here is equal to our negative e to the negative x times sin x plus cosine x. And of course, integrate both sides. Left hand side super cool because this does not cancel. But what exactly is this though? When you see e to the whatever times sine, integration by parts, huh? But no, I will show you guys how we can deal with this very nicely. Have a look. When we have the integral of negative e to the negative x times sin x plus cosine x, this is actually super nice. We can actually just look at a u sub. Let u equal to negative x, then we see du is equal to negative dx. So we have this negative dx here. So we can take this into the u world. It becomes the integral e to the u times sine, well, x is going to be negative u, and then plus cosine of negative u in the u world. So that's so good. Furthermore, because sine is an odd function, we can actually put a negative to the front, and because cosine is an even function, this negative doesn't matter. So in fact, we're just looking at the integral of e to the u times negative sine of u plus cosine of u. This is actually so nice because we're integrating e to the u's power times the function plus its derivative. What's the function though? Cosine x. Well, u in here. So in fact, this right here, you can just look at it and then you can just put down this is e to the u times cosine u. It's pretty much the same idea here. Check this out. If you differentiate this, you keep the first function, which is e to the u, times the derivative second, which is negative sine u, plus the second function times the derivative of the first, which is e to the u. So again, this is the result of the product rule for these two functions. So finally, we can see that the answer for this integral is just e to the negative x cosine of negative x. But again, the negative inside of the cosine doesn't matter, so it's just e to the negative x cosine x. So that would be the right hand side. We have e to the negative x times sine x plus cosine x. And then we have this v. V is just y to the negative 1. So let's write that down. And then on the right hand side, we saw that it was equal to this. So this is equal to e to the negative x times cosine x. And right here, right now, let's go ahead and put down the plus c. We're almost done. I'm going to divide both sides by y to the negative 1. So it becomes y to the positive 1. But I'll write that down first. So we have y to the positive 1. And I'm going to divide this to the other side. And then I'll write that down. So we have e to the negative x times sine x plus cosine x over this guys. So e to the negative x times cosine x plus c. Unfortunately, we cannot cancel this and that out yet. But don't worry, we have this initial condition. Y of 0 is equal to 1. So 1 is for y, and then e to the negative 0 times sine of 0 plus cosine of 0 over e to the negative 0 times cosine of 0 plus c. This is 1, this is 0, this is 1. So we have 1 equals 1 over, this is 1 plus c. So c is again equal to 0. So meaning we don't have that. And now we can cancel this and that. So finally, I'm just going to do this in your head. We can c is 0. Cancel this. Let's just say c is equal to 0. Yeah? This is equal to 0. And this and that cancel out. Okay? And then split the fraction. What's this? Tangent x. What's that? 1. Ladies and gentlemen, y is equal to 1 plus tangent x.